So today our speaker is Shaukat Ali. He's a chief research scientist and the head of department at Simula Research Laboratory. His research focuses on devising novel methods for the verification and validation of cyber-physical systems. And he has been involved in several basic research-based innovation and innovation projects in the capacity of PI and co-PI related to testing, search-based software engineering, model-based system engineering, and recently also on quantum software engineering. So I'm really excited for this talk, and without further ado, the floor is yours.
Thank you, Francis. It's a very nice introduction. So yes, so I prepared this this presentation to basically cover different aspects. So I will first see what I'm going to cover. So I will probably you will not be aware of my department at Simula, so I will say a few words about it. And then what kind of quantum software research that we plan to do in the coming years, for which we already have secured funding. And then I will also tell why it is important to have these new methods for quantum software development. And then I will present some of the preliminary experiments we did to test some quantum software. It's a very preliminary and simple work we did, but just to get started on this direction. So at my department, we are working on the development of software systems such as cyber physical systems, Internet of Things in different domains. And we cover different phases, for example, how to engineer the requirements, how to design and develop the system, testing, debugging, and so on. So we cover different phases of software development lifecycle, and we apply different methods such as modeling is one of the key thing we do. We also working on digital twins, which are like replica of the systems, and search-based algorithm, for example, genetic algorithm. And we are applying a lot of machine learning techniques such as rule mining, reinforcement learning. But most of the thing that we do is the application of these algorithms into software system development and testing and so on. And this is the new area, which is quantum software engineering, which we started to look into a couple of years ago. And this is what I will focus in my presentation today. So in the department overhead, if you look at overall view, it's mainly two scientists, is Tao Yue, my colleague, and myself. And then we have a couple of PhD students which are graduating this year. And then we have quite a bit of new hiring which is taking place. We have 8 PhD students, 3 new postdoctoral fellows, and so on. And Tao is also affiliated at in China in Nanjing University of Aeronautics and Astronautics. So she also have a quite big team here. So together we are quite getting quite big in different topics that I mentioned. And we collaborate a lot in Asia, in China, and also in Japan. And we have quite a bit of collaborations in Europe through European projects, and also direct collaborations such as University of Porto and so on. So recently we started to look into quantum software research in our department, and mainly these are two people that we are involved in quantum computing. As I mentioned, my colleague Tao Yu and myself, and we are looking into these areas, which is quantum software engineering, including software modeling, coding, testing, and debugging. And also we are looking into quantum search and optimization for classical software systems. And our research director, R. Magnus, he's investigating into HPC aspect of quantum computing. For example, how can we leverage, for example, national experimental exascale computing infrastructure for hosting quantum computer emulators for different experiments and so on. So this is roughly the setup we have initially now at Simula for in quantum computing area. And I do know that there are some of my colleagues in the networking department who are also started to look at quantum networks. And there are some people in Simula at Bergen who are also trying to look into cryptographic applications of quantum computing as well. So our focus is on doing this new research on how to cost effectively develop quantum software for real world practical and dependable quantum computing applications, which are beneficial to society and industry. So it means that we want to help people with new methods so that they can easily develop safe and reliable quantum computing application, which are based on quantum software. So in terms of active research activities, so these are the research activities I will briefly mention, that for which we have either some external funding or we have some internal strategic funding to support these activities. And we hired a few PhD students who will hopefully start soon to help us with these activities. So we're working on quantum software testing foundations for quantum programs, which are independent of programming languages. So it means that you write your program in Q#, or you can write your program in Qiskit, and so on. But the testing foundations, I mean, the basic theories remain the same: how to effectively test and find problems in or faults in quantum programs. And in this, we are also looking for, since as we say, as I think Franz mentioned, that IBM was testing this 10,000 qubits. So if you have a simple program like 10 qubits, 20 qubits, you can try to run all possible inputs, and you can check that if your program is giving you your expected output or not. But when the number of qubits will increase a lot, then it means you need to do some sort of optimization. So we are looking into different versions of genetic algorithms and so on to optimize test cases for quantum programs. So we published one very initial work with our master student, Shinji Wang, the third author here, and where we try to assess how the inputs and outputs of quantum programs can be used to test some aspect of the quantum program. So I will focus on this work later on in more details, because this is what we have done more concretely so far. And then we also looking into this tool on mutation testing. By mutation testing, I mean that when we design test cases, let's say I have 200 test cases for a program, but we need to see that how effective those test cases are in finding different kind of faults in the quantum programs. So it's very, so right now, because since we are very early, so we don't know what kind of faults that exist in quantum programs, so that we can actually see those kind of faults in the quantum programs to assess the effectiveness of the test cases. So mutation testing is a technique that is commonly used in software testing to assess the quality of your test cases and testing techniques. So we'll make this tool available in July so that people can derive different faults in quantum programs, and then you can run your testing techniques to assess the quality of your testing techniques. So in these topics, we have hired 2 PhD students who will start in one in June and 2 after summer, who will help us on these topics. And we also have one Erasmus student working on this mutation testing tool, and one master student working on also on this topic.
Can I ask a quick question?
Yes, of course.
So if you talk about these faults, do you think about like bugs that are implemented sort of unintentionally in the wrong way, or is this like errors that or noise that comes from the environment?
So right now what we are looking into is the first case. So for example, as a developer, when I write some code, I can make problems. I can introduce some faults. So we right now we are focusing on those faults, but we have to somehow extend these testing techniques to also consider those errors in hardware as well, because right now we have quite a lot of noise in the hardware as well when we try to run those testing techniques on actual quantum computers. So right now the focus is that when, as a developer, if I write a code, I can make faults, and then our aim is to find those faults.
Okay, thank you.
And then second area, we are looking into quantum software development. And we have a one PhD student who will work on that. And I'm not sure if you guys are familiar with language called Simula. It was built in 1960s, and it was first object-oriented programming language. And actually Simula Research Lab was named after the 2 Norwegian scientists who built this language. And in 60s, this was the language who built this foundation of object-oriented concepts. And now these are widely used to build various programming languages. After like 60 years, these concepts are being used. So the main research question that PhD student will investigate is what could be that kind of paradigm for developing quantum programs. And so that it needs to be very intuitive, it needs to be effective, and that should make more sense for people, because right now we are doing a lot of programming on on the circuit levels, we are doing a lot. Maybe we have some libraries and so on as well, but we are still at very low level. So can we think about some programming paradigm that will help us to write programs more efficiently and without any problems and errors in the code? So this PhD student will going to work on the development of this paradigm. And then we have one student who will work on debugging. It means that in our testing techniques, we aim to find the faults that developers did in the code. Let's say with testing techniques, you can only find that your program failed or not. So this means that then you need to somehow automatically find where the fault is and how to easily fix it. And it's very challenging as compared to classical program, because in classical programs, I can put checkpoints at various locations, and then I run my program, I stop, I check the value of the variables at each checkpoint and so on. In quantum programs, we cannot do that, because if we do that, if we try to read, we will lose superposition. So it's a very challenging to automatically debug quantum programs uh, without violating some properties of quantum programs. So it's so our this PhD student will work on coming up with new tools to automatically bug finding their location and how to fix them. And we have one master student who is trying to look into how to build these abstractions on top of programming languages. So, for example, I'm not sure if you're familiar with Unified Modeling Language (UML). There are also a lot of modeling languages used in industry, for example, in Simulink and so on, which allows you to capture concepts at high level of abstraction so that you can do different kind of analysis, such as model checking, code generation, testing, and so on. So one master student is looking into coming up with some sort of these abstractions on top of quantum programs. And we did some initial work together with my colleague and in a workshop to initiate the idea. And yeah, this was the work. So just to now build why we need, just to give you some, because when I talk to a lot of people, they still ask me, so why it is important to develop testing methods, why to do software development methods. A lot of time this is question. So I just wanted to put some arguments maybe to convince people that why it is important and why we need to look it around. So if we look, we have a lot of software around. Airplanes have, for example, 6.7 million lines of code. Cars have millions of lines of code. Operating systems have a lot of code. Google services approximately have 2 billion lines of code. And now we are thinking to put quantum software in a lot of these kind of critical applications, because we want to make very useful applications, real world practical applications with quantum software. But since the software is all around, and then quantum software is going to be more and more in the future, hopefully pervasive and everywhere. So it means that when software is there are going to be the failures. For example, I give some example that, for example, in 2014, 11 million people were affected due to a software bug in 9/11 emergency services. June 2014, 20 inmates were released because of a software fault. There was another problem in the Obamacare system in 2013. There was another bug because of which they released some prisoners. There were problem with the lawyer software, and was a clash in F13 software. And if you can easily find that so many problems with the software all around. So, and if you're following, for example, Mars helicopter Ingenuity, there was some problem as well in their very few lines of code that tell them, okay, there is something wrong, but actually there was not something wrong. So I stopped following after that, but I think this clearly shows that software is going to be everywhere. It's going to be a problem if we don't ensure its quality and we don't test it properly. So thus we believe that there is a need for software development methods which can help us to develop complex quantum software-based QC applications which are dependable. By dependable, I mean they're safe, reliable, they don't crash, they don't affect people's life, or they don't have any consequences on the environment, on the systems, and so on. That's why we believe that we need to right now start thinking about this quantum software development. Because if we look back a long way in 60s and 70s, 1960s and 70s, when systems started to go more and more big, huge problems, then people started to realize why we need to think about this from the scratch, from a very beginning when we start developing the software, how to make software more safe, right from the beginning instead of building something and then later on thinking about how to make it more safe. So if we don't do the same thing and we try to right now start thinking about in parallel to as quantum computing community is being developed, in parallel we need to start thinking about these methods and develop some method in parallel to it. This is what we think. So then I think I will present some of the initial experiment we did on testing some simple quantum programs, and we call it quantum input output coverage. And this is inspired from a classical computing where you simply do some inputs and you check the outputs. So it is not something very novel here. It was just a master project to start understanding how quantum program works. So what is an input of quantum program? This definition can vary too. So what how we view is that, let's say this is my quantum circuit, and initialization of this can be considered as one type of input. But this is a very restrictive definition. We can define the inputs in a very different way, but we did some experiment. Let's say we assume that if we can initialize quantum bits, this is called an input. I can get input, and then there could be some output, and output are when I read after the measurement. So you can see that we are trying to treat a program as totally black box. We are not touching anything inside the circuit. So we just give some input and we check if the output is according to what we expect the program to do. And it's very restrictive definitions. So, and then a specification. So when, even in a classical programs, when we need to, when we have a program, we need to have some sort of specification that what the program does. So for example, there could be some input. So if we have all the input, let's say 2000 inputs, it could be that the program is designed to operate only 200 of them, for example. So these are called valid inputs. So we can say that, okay, these are the set of valid input. And in some case, all the inputs could be valid too. So it again depends on the specification of the quantum program. So input values that are valid according to specifications and valid output values, then those are the values which you expect to see from the program when you execute. And in this case, we are checking the program after the measurement. So it means that we have to read it and we destroy superposition. So it means that it's just the output we observe. And as quantum programs are probabilistic, so it means that each output can have associated expected probabilities. So for example, I could observe 0, 10% of the time, to maybe 3, 20% of the time, and so on. So we can have associated probabilities with the output. Just to give a very simple example. So if you see that, let's say for my program, there are two valid inputs, 0 and 1. And for each valid input, let's say that I observe 0 50% of the time and observe 3 50% of the time. Similarly, when the valid input is 1, I observe 0 50% of the time and 3, for example, 50% of the time. So these are my valid expected probabilities associated with program. And it's a very simple program just to show the idea that how it works. So now, so below you can see that in the table that this is my program specifications. So I can say that my valid input is only 0 and 1, and my valid output are 0 and 3 with 50% chances of observing. And of course, when we run the programs, those things will vary because this is theoretically, I know that this is the ideal situation. And when we run the programs, we might observe some deviations. This is one of a simple program written in a JavaScript based language. For example, here we initialize our quantum program to 0. So this circle notation shows that right now we are not in superposition. So it means that all the values are 0. So it's 0. Now I do this Hadamard. So I go into superposition. So I go into superposition of 0 and 1 state. Then I do this C naught, which is conditional not, and then it becomes like this, the state of the program. So the circle notation, it shows that the field part is, if we take the square of that field part, it shows the probability of the program in being that state if I read it. So now if I try to read, I can either observe 3 or 0. This is how the program is working. I'm trying to test it. So what are the challenges? There are a lot of challenges. First of all, is probabilistic nature. It's not typical that I give input and I get output and that's it. So I have to run my program many times to reach some statistical conclusion that if my program is correct or not. It is also very difficult to estimate if you want to test the state inside the superposition. It is very difficult because we don't want to touch it. How to do that? This is a big challenge. And right now, I think we tested very simple program. So we can specify that, okay, 50% of the time the output should be 0, 50% of the time the output should be 3. But ideally, for a complex program for 2000 qubits or 10,000 qubits, we can never define very precise test oracles. And by test oracle, I mean expected outputs. So it means that this is again a very big challenge that we still need to address, how to deal with this kind of precise oracles. So what we did was that we have a very simple framework. We do different kind of coverage, 3 coverage criteria. We have 2 type of test oracles. And then we do the assessment based on this mutation technique I mentioned to see that how effective these 3 coverage criteria are in finding different faults. So I will now go through the details of each of them. For example, first is very simple, which is called input coverage. So it means that in my test suite, a test suite consists of a set of test cases that for each valid input, I should have at least 1 test case. And we can statically generate this one. So just look at the example. This was my program specification. So the possible test suite according to input coverage is that input 0 and input 1. So it means that I need to run my program with input 0 and input 1 because these are my only 2 inputs for this particular program. So then I can achieve input coverage. So it means that input coverage is that I want to execute my program with exactly each valid input. Now, if I move to output coverage, it means that with my test suite, I want to observe each valid output at least once. And for this criteria, of course, since we're talking about the output, so it means that I have to execute my program to observe the output. But in case of input coverage, I statically know that what is my test suite, just 0 and 1. In this case, I have to execute a program certain number of times to observe the valid outputs. Again, this was the same program specification. So possible test suite in this case would be if you see that input is 0, 1, 0, and the output is 0, 0, and 3. So when we reach 3, it means that the valid output was 0 and 3. So it means that at this point, we have achieved output coverage. This is the second coverage we tried. And then third is that input output coverage. So it means that for each input, I want to observe each valid output. And of course, in this case, since we are relying on the output, we have to execute the program to see when we reach the specified coverage. Same program. So in this case, for example, you can see that for each input 0 and 1, I have to observe output 0 and 3. So when I do that, it means that this is my complete test suite. So for each input, I want to observe each valid output in this case. So these were the 3 criteria we defined to see what is their effectiveness in defining different kind of faults. Then of course we have inputs, how to cover different inputs. Then we need to see that whether my outputs are correct or not according to specification. So we need this thing which is called test oracle. So we define 2 test oracle. First is called wrong output. It means that if I run the input and observe something which is not correct according to it, then I stop. That's it. So it's definitely fail. So an example is that in this case, we see that the valid output has to be always 0 and 3. Let's say I run the input with 0 and I observe output 1. So it means that the output is wrong. So I can stop my program right away because this is not what I expected my program to do. So I did some problem in my code. The second output is probabilistic, which is called output probability oracle. It means that the program gives me the correct output according to the specification, but then I need to run a certain number of times to compare it with expected probabilities. For example, 50% 0, 50% 3. So I need to compare it with them. So to do that, I need to run it many times. And then it will tell me whether I have likely failed the program or I cannot conclude anything, for example. And to do that, we do statistical tests. So for example, this is my valid input I according to program specification, and I get a valid output according to a probability. Then we observe. So on the top, you can see that the probability was the one which was specified according to program specification. And below, when we execute the program and we observe the probability, and then we compare these two. And we see that how different they are according to a statistical test. So just to give example, something like this. So in this case, let's say that, so this graph on the y-axis, it's the probability, and then these are the two different test suits, for example, group 1, group 2, group 3. And we observed that we always observed 0, but 0 was observed never, and 3 was observed 100% of the time. It's a very extreme example. It means that every time I execute the program, I only observed output 3, which is not correct according to C, because I only want to observe 50% of the time 0 and 50% time of 3. And when I do this statistical test, it will give me a value less than 10 point, very small p-value, which tells me that this is too different. Then it means that my program is likely failed, because it's the specification according to probability doesn't match. And in another case, for example, we have different values, different number of zeros and ones, and then if the p-value is greater than 0.01, it means that there is no significant difference. So it's kind of inconclusive. So we cannot say that it's pass or fail. So we mostly can say inconclusive. Now the mutation operator, what I mean. So it means that we need to, so when I'm writing some program, I can do some mistakes. Since we don't have at this moment any repository that exists that tells what kind of problems actually programmers do when they write quantum programs. So we took a very simple approach, which is called mutation operator. So it means that add gate. We add a gate to the correct program to do one fault. So for example, if this is my correct program, I add another Hadamard, for example, on qubit 1. So this is now my mutated program. So this is a fault that I introduce, and then I run my test cases on it. I need to see if my test cases find this fault or not. And similarly, you can delete a gate, you can replace one gate with another equivalent gate, and so on. So in this way, you can define different kind of faults in the program, and you run your test cases, and you see if your test cases are good to find those kind of faults. And then we picked some programs. They were quite simple programs. Then we generated 2,000 test cases. With each test with 100 test cases. These are some of the typical parameters we used. And right now, there's no guidelines how to select these. So we need to do more experiments to come up with what should be this number. And to calculate the p-value, we use one sample Wilcoxon test with 99% of confidence interval. So mutation score is basically, it's just formula. It tells you that how many, so let's say if I have 100 mutated faults with add, remove, and those kind of gates, I just need to simply see that how many of those were found by my test cases. So we call this mutation scores, which help us to find that how effective my test suits are in finding those faults. So we use this term, which is called mutation scores. In terms of cost, we look into how many test cases we need to kill the mutant. By killing the mutant, I mean that I run a test case, I see if I found the fault or not. And then we also checked, because we have two types of oracles, we can also calculate how many test cases were needed in each type of oracle to find faults. So mutation score is more, tells me the effectiveness of my coverage criteria in terms of finding faults. Cost tells me that how many test cases I need to find faults. So we evaluated effectiveness and we also evaluated cost. Some of the results, when we don't differentiate between the two types of oracles, we see that it managed to achieve more than 80% of mutation score with various costs. But you can see that in the number here, for example, 2001, 2397, 122 is the number of test cases. You can see that input coverage is quite simple, but as we go for output coverage, we go input-output coverage, the number of test cases are too many. Similarly, for other programs, we managed to achieve 80%, 95% of mutation scores. And you can see the average number of test cases, which are quite increased when we go to output coverage or input-output coverage. And so on, something like this. So what we observed is that with the very less expensive, less number of test cases with input coverage, we can still achieve good mutation scores. And if we use more expensive criteria, such as input-output coverage, we may increase mutation score, but we need to see that the number of test cases has increased a lot. And it means that it is more costly to apply this approach. So when we consider two types of test oracle, we can see some results like this. So woo was when we observe the wrong output. So we can clearly see a pattern that when we have wrong output, when the program is too faulty that it always produces wrong output, it's easy to find it. On average, 1 or 2 test cases, you can find that problem. But when, of course, when the program is giving correct output, but then we need to compare the probabilities, then the number of test cases is quite high. So our key finding was that it's wrong output, it's quick, but if it's, then we need more number of test cases. And of course, what we were thinking is that we can set some time budget as well if we need, because if it's according to OPO, which is observing the wrong probabilities, then it's depending on your cost, you can say, let's say I only want to test for 10 minutes, for example, that's it, stop it after that. So we can also set up this kind of time budget as well. So we find that, of course, our approach has scalability issues. So if I have 8 qubits, I can do all the input coverage very easily. But you can see that when I was trying to do input output coverage with few qubits, number of test cases was more than 100,000. And if I have to run 1,000 qubits, maybe it will be crazy to run these criteria. So it means that we need to look into more test optimization, and actually did some work recently on where we applied genetic algorithm and we tried to reduce the number of test cases. So we submitted this paper to a conference. So I didn't discuss it here because the conference requires double blind review. So I don't want to mention that here, but and we didn't deal with a lot of the phases in the qubits, and mutation analysis need to be improved. It's very brute force at the moment. We generate all possible mutations and we test, which is not a good approach. So we need another method to find more difficult mutations so that we can only focus on those instead of generating thousands and thousands of mutations that are all possible. So this is it, and then that's all from me for now. So yeah, if you have any question on any part, please just ask me now.
So first of all, thank you for the nice presentation. And I guess I have one question to begin with, because if you test something without output and you have, then you need to know the statistics. And that sort of means that you have to know what the program is doing, right?
Yep.
So if it sort of limits the oracles or the black boxes you can test, right?
Yeah, this is I think one of the challenge I mentioned, that this is a very big challenge because if for a very simple program that we tested, we could come up with the specification because we knew. But when the programs are going to grow a lot, it will not be possible to have very precise specification. So either we will have some sort of partial specification, or in our domain, we also use this testing, which is called metamorphic testing, where we try to learn over the period of time the correct specification. I haven't tried it yet, but the plan is to look into metamorphic testing to deal with this oracle problem that you are mentioning. It's a very big problem. So that's why this approach is very limited. If we have to deal with complex program with many qubits, it will not work. So because when we start to do, it's impossible to find very precise I mean, for example, I was saying 50% 0, 50% 3. But if I have all possible inputs, all possible outputs, it will be kind of impossible to know what the correct program, what the program should have. Because especially, for example, if I write a new program, and then if I need to specify, I don't know, because I cannot even execute because I might have done some coding error myself. So it's a big challenge that we need to address in our works in the future.
Yes, I mean, I guess one thing is to just test the hardware with this, right? Particularly if it's, because then you can create like a uniform superposition or a complete entanglement or something, and then it's quite challenging to actually achieve this position, but you know perfectly the outcome, and the outcome is sort of yeah, it's not exponentially hard to get the statistics, because that's another thing, right?
Yeah.
So if you need to do exponentially many measurements to get the correct statistics, then you're sort of doomed to begin with.
Yeah, exactly.
Yeah. Yeah, maybe are there any more questions? So you're free to speak or raise your hand or chat.
Just a short question. I'm not sure if I understood this story about the mutations. So is it just the basics? I mean, are you saying that suppose you have a program, it's not working, it's not doing what you want it to do, then I add a random mutation and I see if it gets better? Was that?
No. So what I was saying that right now so I have a so right now the issue is that we don't know that what kind of faults people will do in the quantum program when they are writing. And in our case, we wanted to evaluate how effective my coverage criteria are.
You're creating faults to test
Yes.
your
Yes.
diagnostics.
Exactly.
Okay, good. Yeah.
Are there any more questions?
I'm not really sure if I know how to ask my question.
You can give it a try.
Yes.
Yes, and show my ignorance. Yes, I always have a hard time of seeing the difference between the hardware and the program here. So, is it an instance of the hardware we are testing for faults, or is it a program? By program, I mean something that is possible to do in modules, and if each module works, then the total program will work.
Yes. So right now it's the program.
It's the program, yeah.
Yes. So we can divide into different modules, as you say, and as well. And right now we are not even we are not doing testing on the hardware. So we are just running them on simulators by assuming that the qubits are perfect at the
Yes.
moment, of course. But and we have these programs which are circuits and in Qiskit at the moment, and you can have different methods. You can have different parts of circuits and use. So it's more like when people are designing their circuits in Qiskit, we want to make sure that those are correct.
Yes. Thanks. I think I got that.
Okay, so if there are no more questions, then thank you one more time. And yes, I will stop the recording.